Welcome to the deep dive. We sift through the latest research, the most fascinating ideas, and basically give you those essential nuggets of knowledge. Today, we're plunging into a realm that honestly feels straight out of science fiction, but it's rapidly becoming reality. Brain-computer interfaces, or BCIs. Just imagine for a second being able to control, say, a robotic arm simply by thinking about moving your own. Or maybe communicating complex ideas directly with a computer, completely bypassing speech or keyboards. We're really talking about unlocking entirely new ways for our brains to interact with the world around us. It's pretty mind-bending stuff.
It absolutely is, and the potential applications, particularly in the clinical space, are just enormous.
But like with most revolutionary visions, there's a catch, right? This incredible transformative potential harbors a really significant, often unseen engineering challenge. As these BCIs get more sophisticated, they rely on, well, increasingly high-density neural recordings. You need more data for more precision.
Exactly. More data means more nuance, more potential for complex control.
But it also translates into a truly massive torrent of information. I mean, just to give you a concrete idea, picture a BCI system with maybe 124 channels. Think of them like tiny listening posts in the brain. And each one is sampled at, say, 30,000 times per second, generating 16 bits of info per sample. Well, you do the math, you're looking at a staggering 491.52 megabits per second of raw data.
That's an immense amount of brain activity to capture.
Right, and trying to wirelessly transmit that raw data, especially from a tiny device nestled within or on your head, that presents huge challenges. We're talking about fundamental limits like, finite communication bandwidth, and maybe even more critically, the very real problem of excessive heat generation within these tiny, constrained, implantable devices. It's like a literal data deluge that could quite literally cook the solution before it even starts helping.
The heat problem is non-trivial. You absolutely cannot risk damaging brain tissue. It's a major safety constraint.
So who's the hero stepping up to tackle this massive challenge today?
Well, it's a novel neural signal compression scheme, and it cleverly leverages something called Convolutional Autoencoders, or CAEs, and these CAEs are implemented on an incredibly energy-efficient, purpose-built TinyML accelerator, which has the cool name Ramen.
That combination, the CAE algorithm and the Raman hardware, is the key.
Exactly. This groundbreaking duo promises to overcome these serious data bottlenecks, making high-performance BCIs not just some distant dream, but actually a practical, safe, and really effective reality. So our mission today is basically to give you a clear, concise, hopefully captivating shortcut to understanding how this cutting-edge tech works, why it's so critically important for the future of BCIs, and maybe uncover some surprising facts and clever insights that make it genuinely groundbreaking. We're going to try and unpack the brilliance behind this innovation, piece by piece. And that unseen challenge you mentioned, the data problem, it really is absolutely central. Without a breakthrough like efficient compression, the huge promise of high-density recordings, the very foundation for precise, complex decoding, well, it would largely just remain theoretical.
Yeah.
Especially for the real-world implantable applications we're all aiming for. This work is really about bridging that gap between theory and practice.
That's a really powerful way to put it. It sets the stage perfectly. So let's start with the basics, maybe for listeners who are newer to this field. Brain-computer interfaces. What are they fundamentally, and how are they changing things?
Okay. At its very core, a brain-computer interface, or
Yeah.
BCI, is a revolutionary system. It's designed to facilitate direct communication between the brain and some kind of external device. Think of it like creating an entirely new pathway. It bypasses our usual routes, like motor nerves or sensory organs. It allows your intentions, which are derived directly from your brain activity, to control things. That can be anything from a sophisticated robotic prosthetic to simply moving a cursor on a computer screen.
So thought becomes action directly.
In essence, yes. And the clinical applications are incredibly diverse and, frankly, they offer profound hope. They provide inventive solutions for communication, control, rehabilitation, especially for individuals facing severe neurological challenges. I mean, consider someone who's lost the ability to move their limbs due to a spinal cord injury, or maybe someone who can't speak because of a condition like ALS. For them, BCIs can genuinely be a lifeline. We're seeing incredible progress in restoring lost motor functions, allowing people to regain control over assistive devices just by thinking. And it goes beyond motor control, too. BCIs are also exploring ways to restore lost sensory abilities, like vision or hearing, using targeted neural stimulation based on external sensors.
Wow, restoring senses, too.
Yes, it's a major area of research. The overarching goal, really, is to seamlessly interpret a user's intentions directly from their brain activity and then turn that thought into action or perception. It's about restoring agency, connection to the world for people who might otherwise be, completely isolated.
That potential to restore independence is just
Yeah.
truly transformative. And to get that level of precision, that detailed understanding of someone's intention, you need incredibly rich, detailed information from the brain, right? Which brings us back to how far these intracortical neural recording systems have come. It feels like we've leaped from pretty simple sensors to something vastly more complex.
We absolutely have. Intracortical systems where electrodes are placed directly within the brain tissue have undergone a really dramatic evolution. In the early days, you had groundbreaking devices like the Utah Array. These were hugely important, supporting maybe up to about 100 recording sites. They gave us that first real glimpse into directly accessing neural signals for control. Foundational work.
100 sites, that sounds like a lot already, but compared to now,
Exactly. Compared to today, it's almost quaint. State-of-the-art high-density electrodes, like the ones you hear about from projects like Neuralink or NeuroPixel, they boast thousands of recording sites. Thousands. Imagine the difference in data richness. It's like upgrading from trying to understand a conversation by listening to just one person whispering to suddenly being able to hear every single voice and nuance in a huge crowded room. This exponential increase in recording sites is phenomenal for the potential of BCIs. It means we can achieve far greater accuracy, we can decode much more complex intentions because we're capturing simultaneous activity from a much larger, more representative group of neurons. We get much richer, more complete picture.
more data, better picture. Makes sense.
And this is the crucial, but this very advancement, this explosion in channel count, is precisely what generates those massive amounts of neural data we talked about at the start. All this data then needs to be wirelessly transmitted, usually for offline analysis and decoding on a separate computer. So while we're getting unprecedented insight, the problem of just managing that data, transmitting it, is only growing bigger and bigger.
And that's exactly where we hit that critical bottleneck again, right? The sheer volume, it creates that dual challenge you mentioned, the finite communication bandwidth for wireless transmission, and that equally problematic issue of excessive healing within these tiny, often implanted devices. Why are these two things such major roadblocks for making BCIs a widespread practical reality? It's not just about making it faster, is it? It's about safety, feasibility.
Precisely. Let's break down the finite communication bandwidth first. Think of wireless transmission like a highway. Even the best highway only has so many lanes. If you try to push too much traffic, in our case, raw, high-resolution neural data, through those lanes all at once, you get a massive traffic jam. Data gets backed up, may be lost. It's a fundamental physical limitation of pushing large amounts of data wirelessly, especially within the tricky environment of the human body. We simply can't stream an unlimited fire hose of information through the air without hitting serious bottlenecks.
Okay, the bandwidth limit makes sense. But the heating, that sounds even more concerning for something inside your head.
It absolutely is.
Yeah.
It's arguably the more critical issue, especially for implantable devices. Any electronic component, when it's working hard processing data, transmitting signals, it generates heat, basic physics. The more power it consumes, the hotter it gets. Now, in the incredibly sensitive and confined environment of the brain, excessive heat isn't just an inconvenience. It can cause irreversible tissue damage.
Damage to the brain itself.
Exactly. That's a huge safety concern, a red line you absolutely cannot cross. So going back to your earlier example, continuously trying to transmit, say, 491 megabits per second of raw data from a 1024 channel system, that would require a level of power consumption that generates way too much heat for safe, long-term implantation. It's a real design paradox.
We need the dense data for precision, but we can't afford the power and bandwidth costs of sending it raw.
Precisely. So to mitigate these challenges, to ensure both the safety and the long-term feasibility of these high-performance BCIs, the data must undergo compression, significant compression. And it has to happen before transmission over those wireless channels. This is exactly the problem this innovation, the CAE on Raman, is designed to solve. It's about sending the essential information, not the entire raw stream.
Right, sending the library summary, the zip file, not every single book individually. That analogy really helps.
That's a good way to think about it. Package the essence sufficiently.
Okay, so it's clear we need compression. Before we dive into the specific CAE solution, maybe let's take a quick look at the existing landscape. I understand there are different ways people have tried to squeeze down this neural data. What are some of the main approaches out there?
You're right. There are different strategies, and the choice often boils down to the specific application and what kind of trade-offs you're willing to accept. Broadly, we can categorize compression techniques into two main groups: lossy and lossless.
Lossy and lossless. Okay.
So on the lossy side, one prominent method is called compress sensing, or CS. The basic idea here is to reduce the dimensionality of the data. You take your input signal, and using a specially designed mathematical matrix, you transform it into a much smaller compressed signal. The great thing about CS is its ability to achieve very high compression ratios. It can really shrink the data size dramatically.
But lossy sounds like you lose something.
Exactly, that's the trade-off. When you try to reconstruct the original signal from that compressed version, there will inevitably be some degree of reconstruction error. You lose some information permanently. For certain applications, these small errors might be perfectly fine. They might not really impede the overall function, but you don't get a perfect replica back.
Okay, so high compression, but some information loss. What about lossless?
Right. In contrast, you have lossless compression techniques. These are designed specifically to guarantee perfect reconstruction of the original signal. No errors are introduced. Every single bit of information is preserved. These techniques often fall into categories like dictionary-based methods, where you find frequently occurring patterns and replace them with shorter codes, or statistical-based methods like Huffman coding.
Huffman coding, I've heard of that, like in zip files.
Yeah, similar principle. Huffman coding is quite clever. It assigns shorter binary code words to the most common symbols or data patterns it finds, and longer code words to the less common ones. This results in a more efficient overall representation on average. But while these lossless methods give you perfect fidelity, their main drawback is that they typically achieve significantly lower compression ratios compared to lossy methods. Maybe 2x, 3x compression, sometimes a bit more, but nowhere near what lossy methods can achieve.
So it's always a balancing act. How much can you shrink the data versus how perfectly do you need to be able to get the original back?
Exactly that. Context is everything. For some scientific analyses, lossless might be essential. For many real-time BCI applications, lossy might be the only practical way forward.
That's a really clear distinction. Now, this specific work we're diving into, it focuses on a very particular type of neural signal, right? Can you explain that for us? Because, as you said, brain signals aren't all the same. I know some methods focus just on spike compression.
That's a crucial point. The brain produces this incredibly rich tapestry of electrical activity, and different signals tell us different things. Many existing compression methods, particularly those called spike compression schemes, deal exclusively with compressing discrete spike waveforms. Spikes are basically the action potentials, the firing events of individual neurons. Think of them as sharp, transient electrical pulses, like a neuron shouting a very brief message. We often talk about single-unit activities, SUAs, if we isolate one neuron, or multi-unit activities, MUAs, if we're recording the combined spikes from a small local cluster.
Okay, so spikes are the individual shouts. What's different about what this work focuses on?
Right. A key aspect of this work is that we are focusing on compressing local field potentials, or LFPs. LFPs are fundamentally different. Instead of those discrete, rapid spikes from single neurons, LFPs represent slower voltage variations, typically fluctuating below about 300 Hz. They're thought to reflect the combined, synchronized synaptic activity of large populations of neurons in a local area.
So not the individual shouts, but more like the background hum or murmur of the crowd?
That's a great analogy, yes, like the collective hum or maybe the orchestral sound of an entire section, rather than individual notes. LFPs have a lower spatial resolution compared to spikes. They don't pinpoint individual neurons as precisely. But, and this is a major advantage for long-term implantable devices, LFPs are generally far more stable over time.
More stable. How so?
Well, they're less susceptible to issues like electrode drift, where an electrode might shift position slightly over weeks or months, potentially losing contact with the specific neurons it was recording spikes from. They're also less affected by things like neuron dropout, where individual neurons might die or detach from the electrode surface. And they're generally more resilient to the tissue scarring that inevitably occurs at the electrode interface over time, which can really degrade the quality of spike signals.
Ah, okay, so that stability makes LFPs a more robust, reliable signal source for devices that need to work reliably for years, potentially.
Exactly. For chronic BCI applications, that long-term stability is incredibly valuable.
That makes a lot of sense, but, for someone who might intuitively think more specific data, like spikes, must be better, does focusing on LFPs mean we're losing out on important information? Why are LFPs particularly important for this work and for the kinds of advanced BCIs people envision?
That's an excellent question, and it gets right to the heart of why LFPs are so valuable, particularly for the approach taken here. While it's true that MUA-based BCIs, focusing on spikes, are often highly effective at decoding specific motor cortex activities, like the precise commands to control a prosthetic arm LFP-based BCIs, actually open up entirely new avenues. They can effectively target higher-level cognitive regions of the brain, places like the posterior parietal cortex. This capability is crucial for enabling more advanced cognitive decoding tasks.
Cognitive decoding, like understanding thoughts or intentions.
Exactly. Things that might involve complex decision-making, planning, abstract thought, rather than just direct motor commands. LFPs seem to carry richer information about these higher-level processes. The key insight here is that LFPs, despite having lower spatial resolution than individual spikes, encode a wealth of valuable information. The information isn't just in the presence or absence of a spike. It's embedded within the continuous, fluctuating patterns of the LFP signal itself. Numerous studies have definitively shown that important behavioral parameters, things like movement intentions, the precise kinematic trajectories of a planned movement, even the type of movement someone is about to make, can be accurately predicted directly from these LFP signals.
So the information is in the continuous wave, not just the spikes.
Precisely. It's not just an alternative. It's often a complementary and, in many cases, more robust source of information, especially for these long-term applications and higher-level cognitive tasks. For instance, imagine trying to predict someone's intention to reach for a cup. While individual neuron spikes might give you the very granular muscle twitch commands near the end of the movement, the LFP signals might reveal the broader plan to reach and the goal of grasping much earlier and more reliably. Because this crucial information is continuously encoded in the raw LFP signal itself, compressing this continuous data stream efficiently without losing that critical functional detail presents a unique and equally vital challenge compared to just compressing discrete spike events. Our method, the CAE, is specifically designed to handle this continuous information-rich LFP data.
Okay, that clarifies why LFPs are so important here. It's about capturing that continuous, richer signal, especially for cognitive tasks and long-term stability. So that brings us squarely to the compression engine itself, Convolutional Autoencoders, or CAEs. Before we get into the convolutional bit, let's just unpack the basic concept. What exactly is an autoencoder and why is it inherently good at summarizing information?
Okay, let's unpack this. The analogy you used earlier, the novel summarization, is actually pretty good. An autoencoder is fundamentally a type of neural network used for unsupervised learning. Its main job is to find the most efficient coding or representation of input data. It learns to take some input, in our case, the raw LFP signal, compress it down into its most essential features, and then from that compressed summary, try to reconstruct the original input as faithfully as possible. The trick is that it learns this by forcing the information through a kind of bottleneck in the network architecture. This constraint compels it to learn only the truly significant features, discarding the noise or redundancy. It's basically teaching a network to copy its input to its output, but under a constraint that forces it to learn the essence of the information.
The bottleneck forces it to be efficient.
Exactly. To break it down structurally, an autoencoder usually has two main components. First, there's the encoder network. This is the part that takes your detailed input data, the LFP signal matrix, and maps it down to that lower dimensional latent space representation. This latent space is the compact summary, the compressed version of the neural signal. It's an efficient code word capturing the critical info. And this encoder is the crucial part that we actually implement directly on our energy-efficient hardware, Raman, right there at the source to do the real-time compression.
Okay, encoder shrinks it down on the device. What's the second part?
The second part is the decoder network. This component takes that compressed representation, that tiny vector from the latent space, and attempts to reconstruct the original input signal from it. Crucially for our BCI system, this entire decoding process happens offline, on a more powerful external computer, after the compressed data has been safely and efficiently transmitted wirelessly. This split is key. It keeps the implantable device extremely low power and compact.
That's a really clear picture. Condense on the device, reconstruct externally, always aiming for favorable reproduction.
Got it. Now, we're not just talking about any old autoencoder. We're using convolutional autoencoders, CAEs. What's special about adding the convolutional aspect? Why is that particularly good for brain signals with their complex patterns across space and time?
You've hit on the key innovation here. Adding convolutional layers makes a profound difference, especially for data like neural signals. Convolutional autoencoders, or CAEs, basically combine the powerful principles of convolutional neural networks, CNNs, with that autoencoder structure we just discussed. CNNs, as you might know, are renowned for their ability to process grid-like data, like images. They do this by identifying patterns and features in a hierarchical way using specialized convolutional layers. Think about how a CNN can learn to detect simple edges in an image, then combine those into shapes, and then combine shapes into recognizing objects.
Right, they're great at finding spatial patterns. Exactly. And for neural signals, which are essentially complex spatiotemporal patterns, they vary across multiple electrode channels, space. And over time, these convolutional layers are incredibly effective. They're designed to learn efficient representations by encoding the input into that lower dimensional latent space, but they do it by intelligently extracting features that span both space, across different electrodes, and time, over the milliseconds within our window. This makes them particularly adept at handling the inherent complexity of neural data, finding subtle but crucial patterns that a simpler, non-convolutional autoencoder might completely miss.
So they learn the important patterns across channels and time.
Precisely. Specifically in our CAE design, we take the input neural signal and first divide it into those 50 millisecond windows. With our 2 kHz sampling rate that gives us 100 individual samples per window, let's call that TW, the actual input of the CAE isn't just a single time series, it's a 2D matrix of size CXTW, where C is the number of recording channels in our implementation, C is 96, matching the Utah array electrodes, and TW is 100 samples. So the input is this 96 by 100 matrix representing 50 meters of activity across all channels. The encoder's job is then to transform this entire matrix into a tiny output vector, specifically a 1 by 1 X shape where gamma is a much, much smaller number than 9600. This tiny 1 by 1 X vector is the compressed data, the incredibly efficient summary of those 96 channels over 50 milliseconds.
Wow, from 96 by 100 down to just gamma values.
Right, and this specific optimized setup allows us to achieve incredibly high compression. The compression ratio, CR, is simply calculated as the original data size, CXTW, divided by the size of the compressed representation. And as mentioned, the paper demonstrates this approach achieving a CR of up to 150 for these LFT signals. Now, here's where it gets really interesting. Achieving such a high ratio for continuous LFP signals, while still maintaining excellent signal quality for reconstruction, that's a significant breakthrough. We're not just shrinking the data, we're doing it intelligently, preserving the information that's actually vital for BCI function.
A CR of 150 is just, staggering. To put that in perspective again, it means you can pack 150 times more brain data into the same wireless pipe, or send the same amount of info using 150 times less power, roughly speaking. The real insight here isn't just the number, it's that this is the key to unlocking BCIs with far greater precision and a much richer understanding of brain activity without hitting those crippling data transmission or power limits. How do they manage that? How do they get such high compression without just losing all the useful stuff? What's happening under the hood in that encoder?
That's a great way to frame the impact, yes. The magic under the hood lies partly in the strategic use of a technique called depth-wise separable convolutions, or DWS convolutions, within the encoder's architecture.
Depth-wise separable convolutions.
Standard convolutional layers, while powerful, can be computationally very expensive, especially when you have many input channels like our 96 LFP channels. DWS convolutions are a brilliant optimization designed to minimize the number of computational operations required while still effectively extracting those crucial features. They essentially split the traditional convolution process into 2 distinct, more efficient parts.
Splitting the work. How?
Okay, first, you have a depth-wise convolution. Imagine you have your 96 input channels. Instead of applying a single complex filter that looks across all 96 channels simultaneously to produce one output channel, a depth-wise convolution applies a separate single filter to each individual input channel independently. So each of your 96 channels gets its own dedicated, simpler filtering process first. This drastically reduces the initial computation load.
Okay, filter each channel separately. Then what?
Then, after this depth-wise step, there's a point-wise convolution. This operation uses standard 1-by-1 convolutions filters that are just 1 point wide and 1 point high, but deep enough to span all the channels coming from the depth-wise step. These 1-by-1 convolutions essentially combine the information from all those individually filtered channels to create the final new output channels for that layer. By splitting the operation this way, first filtering spatially within each channel, then combining information across channels, DWS convolutions significantly reduce the overall number of multiplications and additions required compared to a standard convolution doing it all at once.
Fewer calculations means less power, less time.
Exactly. This is absolutely vital for energy efficiency and speed, particularly in a tiny, power-sensitive implantable device. The real brilliance of using DWS convolutions here is their ability to slash the computational and energy demands dramatically. This allows complex feature extraction processing to happen within the tiny, power-constrained implant rather than needing external, energy-hungry systems to do it. It makes on-device intelligence feasible.
That's genuinely clever, breaking the task into simpler, parallel steps to save energy.
Okay, so once the data is efficiently compressed by the smart encoder using DWS convolutions, the decoder on the other end has the critical job of putting it all back together. What's happening on the reconstruction side, and how do they ensure the signal is accurately preserved given all that compression?
You're absolutely right. The decoder's fidelity is paramount. It essentially performs the inverse operation of the encoder. It uses specialized layers, often called transposed convolutions.
Transposed convolutions.
Yeah, sometimes they're referred to as deconvolutions or fractional stride convolutions. Their main purpose is to intelligently upsample the data, basically expanding that compact, latent representation, that tiny one-by-one vector, back into a signal matrix that closely resembles the original 96 by 100 in plane. It's about taking that efficient summary and reconstructing the novel from it as faithfully as possible.
Making it big again, intelligently. Right. And the overarching goal is the entire CAE system, the encoder and decoder working together, is to minimize the reconstruction error between the original input signal and the signal that the decoder meticulously reconstructs. To achieve this, during the initial training phase, which is done offline, the network uses a specific loss function to measure how well it's doing. The most common choice, and what they used here, is the mean absolute error, or MAE, loss.
Mean absolute error,
Yeah.
MAE.
Yes. This function simply calculates the average absolute difference between every single data point in the original signal and its corresponding point in the reconstructed signal. By continuously trying to minimize this MAE loss value during the expensive training process, the CAE learns how to encode the input data into that lower dimensional representation while retaining the maximum amount of critical information needed for an accurate and functionally useful reconstruction. It's a delicate balance, between achieving high compression and maintaining high fidelity. But the convolutional architecture, especially with DWS layers, is exceptionally well suited to identifying and preserving those essential spatiotemporal features of the LFP signal that matter most for decoding intentions later on.
Okay, so the MAE loss guides the training to find that sweet spot between compression and accuracy. That makes sense. So we have this brilliantly engineered compression algorithm, the CAE. But like you said, an algorithm is just code until it runs on something. And that something is Raman, a reconfigurable and sparse TinyML accelerator for inference on edge. It's quite a name. But it sounds like Raman is basically custom-built hardware specifically designed to be the perfect partner for this really demanding, power-sensitive compression task. Is that right?
That's exactly right. Raman is the bespoke hardware counterpart to our CAE encoder. It's purpose-built for energy-efficient, real-time neural data compression. The term TinyML accelerator is key here. It signifies a piece of hardware meticulously designed to execute machine learning models like our CAE encoder using the absolute minimum amount of power and taking up the smallest possible physical space. Tiny machine learning, TinyML, that's the field.
TinyML, right, and edge computing.
Yes, the edge computing aspect is equally vital. In the context of a BCI, the edge refers to putting the processing power and efficiency right at the source where the data is generated. So, for instance, within a compact head-mounted unit, or potentially even inside an implanted chip itself. This on-device, localized processing is what truly prevents the need to constantly transmit those massive amounts of raw data, which, as we've established, causes those crippling bandwidth and heating issues. Raman's architecture isn't just a generic processor, it's a highly specialized system. It comprises tightly integrated compute units, memory blocks, and control subsystems, all optimized together to achieve this very specific, very demanding goal of low-power, real-time CAE inference.
That idea of processing right at the source, at the edge, seems absolutely fundamental to making these devices practical and safe. You also mentioned earlier that Raman exploits both input activation and weight sparsity. That sounds like a very sophisticated way of saying it's incredibly efficient. What does that mean in practice? How does it save energy and speed things up?
It's all about extreme efficiency, yes. In many deep neural networks, it turns out that a lot of the activation values, which are the outputs of the individual neurons or computational nodes within the network, and also many of the weights, which are the parameters defining the strength of connections between these nodes, end up being zero or very, very close to zero after training and pruning.
So lots of zeros in the calculations.
Exactly. These are what we call sparse elements.
Hmm.
The network is sparse. Raymond's clever hardware design is specifically built to leverage this sparsity. In practical terms, this means that Raymond can literally skip processing cycles whenever it encounters these zero activations or zero waits. Think about it. If you don't have to multiply by zero or add zero, you save energy because you're not doing a useless calculation, and you save time because you skip that step. This directly translates into reduced processing latency, making it faster. And it also significantly minimizes memory access because you're not constantly fetching or writing data that's just zero and doesn't contribute anything. On top of that, the sparse weight matrices themselves can be stored in Ramon's memory much more efficiently using compression techniques, further reducing the memory footprint and power needed for storage.
So it smartly ignores the zeros to save time and power, like efficient accounting.
That's a good analogy, yes. Skipping over the empty entries in the ledger makes the whole process much faster and more energy efficient.
What's really fascinating here, though, is that Raman isn't just clever hardware design in isolation. You emphasized it's a brilliant example of co-optimization, where the hardware and the software or the algorithm are designed together. You highlighted this hardware-aware, balanced, stochastic weight pruning scheme. That's a mouthful. Can you break down what that means and why it's such a big deal for saving memory and power?
Indeed, this hardware-software co-design is a major contribution of this work, and the stochastic pruning scheme is a fantastic example of its ingenuity. Let's break it down. Conventionally, a common technique to make neural networks smaller and faster is called magnitude-based pruning. You basically look at all the connection weights in the trained network, identify the ones with the smallest absolute values, the weakest connections, and force them to zero, effectively removing them.
Get rid of the least important connections.
Right. The challenge with this traditional approach, however, is that even after you've pruned these weights, setting them to zero, you still need to keep track of the non-zero weights.
Yeah.
This usually means storing not only the values of the remaining non-zero weights, but also their indices, basically, their original addresses or positions, so the hardware knows where they belong in the calculations. This indexing overhead can consume a significant amount of extra memory. For instance, previous work might have used 8-bit values for the weights themselves, but still needed maybe 4-bit indices for each non-zero weight just to store these pointers. That adds up quickly.
So you save on weights but pay for it in index storage.
Exactly. Now, the novel stochastic pruning solution developed for Raman completely eliminates this need for explicit index storage. This is a game changer for memory efficiency.
How does it do that? No indices.
Here's the clever part. During both the training of the CAE model, which is done offline, and critically, during its real-time operation on Raman, the inference step, specialized hardware components called linear feedback shift registers, or LFSRs, are used. These LFSRs generate deterministic pseudo-random sequences, or PRSs, on the fly. These sequences of numbers effectively act as the indices.
Generate the addresses as you go.
Precisely. So instead of storing a huge lookup table of indices in memory, Raman simply generates the expected sequence of indices using its LFSR as it processes the data stream. Only the actual non-zero weight values need to be stored sequentially in memory. Raman, using its LFSR, knows deterministically which stored weight value corresponds to which generated index at any given moment. This is truly brilliant for drastically reducing the parameter memory requirements. And the beauty is, implementing the LFSR logic itself requires only a tiny, almost negligible amount of additional hardware resources on the chip. We're talking maybe 32 lookup tables and 20 flip-flops in an FPGA context, incredibly compact. It adds almost no memory footprint. It's deterministic, always generates the same sequence from the same starting point, and it's very low power. It's an incredibly efficient way to get index information without storing it.
That is genuinely elegant. Generate what you need when you need it. What about the balanced part of the pruning?
Yes, the balanced pruning strategy. This is also crucial for performance. When you prune weights, you want to make sure that the remaining non-zero weights are distributed fairly evenly across the different parallel processing elements, or PEs, within Raman's computational array. Without this balancing, you might end up with a situation where some PEs get loaded with a disproportionately heavy workload of non-zero weights to process, while other PEs are sitting relatively idle or underutilized because most of their assigned weights got pruned. This kind of imbalance creates performance bottlenecks and limits the overall speedup you can get from parallel processing. So the balanced pruning strategy specifically ensures that each processing element receives a roughly equal number of non-zero weight elements to handle. This guarantees a consistent and optimal workload distribution, maximizing the throughput and efficiency of the entire accelerator.
That makes perfect sense. It's like a smart choreographer making sure every dancer in the group has exactly the right number of steps to perform, keeping everyone busy and synchronized. It's incredibly thoughtful design. You also highlighted another clever memory optimization: overlapping input and output activations on the same memory space. What exactly is happening there to squeeze out even more memory savings? That sounds critical for tiny devices.
This is another ingenious trick to maximize efficiency and minimize the physical silicon area needed for memory, which is
Wow.
often a big part of chip size and power. In many typical hardware accelerators for neural networks, the memory used to store input activations, IAs, that's the data coming into a processing layer, and the memory used to store output activations, OAs. The results produced by that layer are often physically segmented into distinct memory banks or spaces. So you'd have one dedicated block of memory for the inputs of a layer and a separate dedicated block for the outputs. The total activation memory needed would be the sum of the sizes of these two separate spaces, representing the peak memory requirement.
Separate buckets for inputs and outputs.
Right. Raman's approach, however, intelligently eliminates this rigid partitioning. What happens is this. Once a specific tile, think of it as a small block or chunk of input activations, has been successfully prefetched from the main memory into the processor's local cache, which is very fast memory right next to the compute units. The original copy of that input tile sitting in the slightly slower main activation memory becomes redundant, at least for that immediate processing cycle. At this precise moment, Raman allows the newly computed output activations for that tile to directly overwrite that now redundant input activation memory space.
Reuse the space immediately.
Exactly. It's like having a single scratch pad. You write down your problem, you do the calculation in your head, the cache, and as soon as you have the answer ready, you immediately erase the problem from the scratch pad and write the answer down in the same spot, ready for the next calculation that might yay it. This dynamic memory reuse dramatically reduces the peak activation memory storage needed at any given time. The paper reports this technique achieved a significant reduction of up to 37.5% for models like the MobileNet V1 CAE variant they tested, making the entire system much more compact and potentially lower power because you need less physical memory circuitry.
That's incredibly resourceful. Just dynamically reusing memory as soon as it's free. It really shows how every single bit of efficiency is being squeezed out of this Raman design. Beyond these highly specialized optimizations for sparsity and memory, what else makes Raman a versatile and powerful platform, maybe for future BCI developments or other TinyML tasks?
That's a good point. While highly optimized for this CAE task, Raman's strength also lies in its underlying programmable nature. It's not just a hardwired single-purpose chip, it's designed with flexibility in mind. It supports a wide range of common neural network layer types and topologies. This means it can handle various structures found in modern deep learning. This includes, of course, standard convolutional layers, but also those specialized depth-wise and point-wise separable convolutions we discussed, which are the fundamental building blocks of many efficient network architectures like mobile nets, which they also tested. It also fully supports various pooling operations, like max pooling and average pooling, which are essential for downsampling feature maps and making the network more robust. And it can even handle standard fully connected layers, often found at the end of classification networks. This broad programmability means Raman isn't necessarily confined only to the specific CAE encoder for LFP compression. It could potentially be adapted and reconfigured for different BCI applications, perhaps using different types of neural network models or even tackling future advancements in network design, all without requiring a complete hardware redesign from scratch. This flexibility is really crucial for long-term research and development in such a rapidly evolving field like BCIs and TinyML.
That flexibility is definitely key for future proofing. Okay, so we have this incredibly sophisticated compression algorithm, the CAE, running on this highly optimized, custom-built, flexible hardware, Raman. But the true acid test, of course, is how does it actually perform in a real-world scenario? Tell us about the experimental setup. What actual neural data did they use to rigorously validate Raman's capabilities?
Right, the real-world validation is where the rubber meets the road, where we see if all this theoretical brilliance translates into practical impact. So Raman was implemented and tested on an Ethernet Titanium Ti-60 FPGA. That's an advanced type of chip called a field programmable gate array. Using an FPGA is common in research and development because it allows engineers to rapidly prototype, test, and iteratively fine-tune complex digital circuits like Raman before committing to the much more expensive and time-consuming process of creating a final application-specific integrated circuit, or ASIC.
So FPGA for testing, maybe ASIC for the final product. Makes sense. What about the brain data itself?
For the dataset, they used genuine neural recordings, not simulated data. These were obtained from the motor cortex of 2 macaque monkeys,
Right.
identified as K and L in the study. These monkeys were actively engaged in performing a precise, instructed reach and grasp task. This type of task is great because it generates rich, complex motor control signals that are highly relevant and interpretable for BCI systems aimed at restoring movement.
Real tasks, real brain signals.
Exactly. The neural activity was captured using 96 active channels from a standard 10 by 10 Utah electrode array. This is a widely used and well-understood type of intercortical electrode array in BCI research. The raw signals, which were initially sampled at a very high rate, 30,000 samples per second, 30 KSs, were then carefully downsampled to 2,000 samples per second, 2 KSs, specifically for the LFP analysis. This downsampling focused the analysis on the crucial frequency band for LFPs, which is roughly 0.1 Hz up to about 300 Hz. These downsampled LFP signals were then divided into those 50 millisecond windows we discussed earlier, resulting in 100 time samples per window across the 96 channels. These 96 by 100 matrices became the direct input to the CAE models running on Raman. This rigorous setup ensures that the performance results they got are directly relevant to real-world BCI applications using LFT signals.
That sounds like a very robust experimental setup. Okay, so with all that real-world data running through the system, how did it actually stack up? What were the key performance metrics they looked at? And what were the most impressive numbers coming out of these tests? Basically, how well was the signal preserved after all that compression, and how accurately was it reconstructed?
They focused on 2 primary metrics to rigorously evaluate the quality of the reconstruction after compression. First was the signal-to-noise and distortion ratio, or SNDR. You can think of SNDR as a measure of signal purity. A higher SNDR value, measured in decibels, dB, means your reconstructed signal is much cleaner and closer to the original, with less unwanted noise or distortion introduced by the compression process. Higher is better.
SNDR for signal purity.
Okay. The second key metric was the R2 score, also known as the coefficient of determination. This measures how well the variance in the reconstructed signal predicts or explains the variance in the original signal. An R2 score ranges from 0 to 1. A score of 1.0 indicates a perfect linear relationship. The reconstructed signal is essentially a perfect mirror image of the original in terms of its fluctuations. So a score closer to 1.0 means the reconstruction is capturing the dynamics of the original signal extremely well.
R2 score for matching the original dynamics. Got it. So what were the numbers?
The numbers are indeed quite impressive, and they really speak volumes about the system's effectiveness, especially given the high compression ratios. For compression ratio, CR, their compact, custom-designed model, a DS-CAE1, achieved that astonishing CR of 150 we mentioned. Even a more standard adapted model, the MobileNet V1 CAE, 0.25x, still managed a very respectable CR of 37.5. To put this in context again, these ratios are significantly higher than many prior LFP compression methods, which often struggle to get much beyond a CR of maybe 10 or 20 while maintaining usable signal quality.
So much higher compression. How was the quality? SNDR and R2.
The reconstruction quality held up remarkably well. For the high-compression DSCAE1 model, CR150, it demonstrated a superior SNDR of 22.6 dBs for Monkey K's data and an even higher 27.4 dB for Monkey L's data. These are very strong SNDR values for this level of compression in neural signals. The R2 scores were equally strong, reaching 0.81 for Monkey K and an outstanding 0.94 for Monkey L using that same compact model. An R2 of 0.94 is incredibly close to perfect reconstruction of the signal dynamics. These figures clearly indicate that they're achieving very high compression without a prohibitive loss in the fidelity or the functionally important information contained within the LFP signal.
Wow, CR150 with an R2 of 0.94 is amazing. What about the efficiency metrics? Memory, power, speed?
Yes, those were also critical validation points. The memory savings, thanks to the combination of 8-bit quantization, reducing the precision of the numbers, and that 75% stochastic pruning, were monumental. For the DSCAE1 model, for instance, the memory required just to store the model's parameters was slashed from about 45.76 kilobytes down to a mere 6.19 kilobytes. That's an incredible 7.4 times reduction. And their innovative stochastic pruning technique, compared directly to conventional magnitude-based pruning, contributed up to a 32.4% further reduction in parameter memory size on its own. This directly validates the power of generating indices on the fly instead of storing them. This kind of memory efficiency is absolutely crucial for fitting complex models onto tiny, resource-constrained implantable devices. Huge memory savings. What about power, the critical factor? Power consumption is arguably the most critical aspect for the long-term viability of implants. Raymond showed remarkably low dynamic power figures. For example, it consumed only about 47.91 milliwatts for that high-compression DSCE1 model when operating at a clock speed of 2 MHz. Now, it's important to be clear. Because this was implemented on an FPGA, there's a significant static power dissipation inherent to the FPGA technology itself, which isn't representative of a final ASIC. However, that dynamic power figure, the power used for actual computation, is comfortably within the established safety limits for devices mounted on the head. This suggests that an ASIC implementation which would drastically reduce static power could achieve power levels suitable for safe, chronic implantation. So these results are extremely encouraging for future, truly implantable systems.
Very promising on the power front for future ASICs. And latency, could it keep up in real time?
Yes, absolutely critical for BCI control. The system proved it could process a full 50 millisecond input window, that 96 by 100 matrix, within an impressive 45.47 milliseconds. Since the processing time is less than the window duration, it means the system operates comfortably in real time. It can continuously compress the incoming LFP data without falling behind, which is essential for providing responsive, immediate feedback for BCI control.
Those numbers really do paint a very compelling picture. High compression, great fidelity, huge memory savings, promising power figures, and real-time speed. But, real brains are dynamic. Signals can drift over time due to electrode movement or tissue changes, and signals can vary significantly between individuals. How well do these trained CAE models generalize? Can they adapt to different subjects or to those inevitable shifts in neural signals that happen over the long life of an implant? That seems vital for long-term clinical use.
That's a critical question, absolutely. Any practical BCI system needs to be robust and operate reliably for potentially months or even years in a changing biological environment. The researchers specifically investigated this generalization capability. What they found was very encouraging. They trained models on a combined dataset using data from both monkey K and monkey L mixed together. When they tested these combined trained models on the individual test datasets, data held back from training, they found the performance was similar, or in some cases even slightly improved, compared to models that were trained solely on data from just a single monkey.
So training on more varied data helped it generalize.
Exactly. It strongly suggests a good inherent ability for these CAE models to learn features that are common across different subjects, which is great news because it could simplify the deployment process significantly. You might not need an intensely personalized model for every single user from day one.
Okay, good generalization across subjects. What about adapting to changes within a subject over time, like electrode drift?
They looked at that too, the adaptability. They simulated this by taking a trained model and then exposing it to just a small portion, only 5% of new, previously unseen data during a brief retraining or fine-tuning phase. Even with this very small amount of new data, the CAEs demonstrated effective learning and showed improved performance on subsequent new data. This indicates that the models can intelligently adapt to novel or subtly changing neural patterns without needing a complete, lengthy retraining process from scratch using vast amounts of new data. This adaptability is absolutely vital for maintaining long-term BCI stability and usability. It means the system can likely compensate for gradual changes in the brain or the electrode interface over time with minimal intervention.
That adaptability is fantastic news for real-world deployment. It suggests these systems aren't just a static one-off setup but can evolve. That brings us nicely to the practical workflow. For a real-world BCI meant for long-term use, it's not just a single event, right? It's a continuous process. Can you walk us through the 3 distinct phases of operation they envision? The full life cycle of using the system, from initial setup to ongoing use.
Absolutely. This system is meticulously designed with that practical long-term BCI application in mind, so its operational lifecycle is intelligently divided into 3 key phases. Phase 1 is a training phase. This happens initially right at the beginning, and it's conducted entirely offline, typically in a controlled lab or clinical setting. During this phase, the Raman encoder chip within the user's head unit is temporarily disabled or bypassed. Instead, uncompressed, raw neural data is streamed probably at a lower data rate initially, as real-time processing isn't the priority here to an external powerful computer. This computer performs the comprehensive training of the full convolutional autoencoder, optimizing both its encoder and decoder components together using a large data set from the user. Once this extensive training is complete, the resulting optimized encoder parameters, which have been specifically quantized to save space and pruned using that stochastic method for efficiency, along with the instructions defining the CAE's network topology, are then securely loaded and stored onto Raman's on-chip memory within the head unit. This training phase typically occurs only once at the very beginning, or perhaps much later, if a major model update or retrain is deemed necessary.
Okay, initial setup and training offline, then load the optimized encoder onto Rayman. What's next?
Next, we transition into the main operational mode, the deployment phase. This is when the BCI is actively being used by the person in their daily life. During this phase, Rayman comes alive. It's actively compressing the incoming neural data stream in real time, right there within the head unit, using those pre-trained and stored encoder parameters and network instructions. The highly compressed data stream, remember, CR up to 150, is then wirelessly transmitted to an external system. This could be a small wearable processor, a tablet, a computer, or even a specialized controller for an assistive device. This external system receives the compressed data, runs the corresponding offline decoder to reconstruct the LFP signals, and then performs the subsequent analysis or decoding steps like figuring out the user's intended movement and converting that into control signals for, say, a prosthetic limb or communication interface. This is where Raymond's real-time, low-power compression becomes absolutely critical, enabling that seamless, continuous interaction.
Right, that's the main mode of operation. Compress on device, transmit, decode externally, control device. What's the third phase?
The final phase is the calibration phase. This is essential for ensuring the BCI remains robust, accurate, and stable over extended periods. As we discussed, the properties of implanted electrodes can subtly drift over time, or the neural environment itself might undergo minor changes, potentially degrading the performance of the initially trained model. The calibration phase intelligently compensates for these non-idealities. What's particularly clever here is how efficient it is. It typically requires only a small amount of new raw data collected from the user, maybe about 10% of the amount used for the initial full training, making the calibration process relatively quick and unobtrusive. And crucially, during this calibration phase, the Raman encoder parameters stored within the head unit remain completely static. They aren't changed. Only the external decoder, running on the offline computer, is retrained or fine-tuned using the small set of new raw data alongside the corresponding compressed data generated by the unchanged encoder.
Ah, so only the external decoder gets updated, not the implant.
Exactly. This brilliant approach eliminates the need for any complex, potentially power-hungry training processes to happen within the implanted or head-mounted device itself. This periodic, lightweight calibration of just the decoder ensures that the model's overall performance remains high, accurate, and stable throughout the device's entire operational lifespan, providing reliable assistance to the user without needing invasive updates to the implant.
That is a really comprehensive and well-thought-out solution, covering the whole life cycle from training to deployment to long-term calibration. It sounds incredibly practical. So let's put it all together now. What does this all mean when we put it into the broader context? Comparing it to other compression schemes out there, why does this CAE-based approach, combined with the ingenuity of Raman, truly stand out as a potential game changer for BCIs?
This is where the innovation's true significance really crystallizes, I think. When we rigorously compare the CAE on Raman scheme to prior works, particularly those that also focus specifically on LFP compression, the results are quite stark. As we've emphasized, it achieves a significantly higher compression ratio, up to 150, than most previous LFP compression methods. Many earlier attempts, perhaps using simpler autoencoders or other techniques, often struggle to surpass a CR of 20, maybe 30, while maintaining acceptable signal quality. A key reason for this superior performance is that our approach, using these sophisticated convolutional autoencoders, uniquely compresses the data in both the spatial domain, across channels, and the temporal domain over time simultaneously. Some prior autoencoder methods for LFPs only really compress the spatial domain, effectively just finding correlations between channels. This dual-domain compression is more powerful and is precisely why it achieves such a superior CR. And crucially, this doesn't come at an unacceptable cost to quality. As the SNDR and R2 scores showed, the reconstruction quality remains remarkably high, even at that CR of 150. We're getting much more data reduction with surprisingly little fidelity loss compared to previous LFP methods.
Better compression and better quality for LFPs.
Yes, and it's also important to circle back to that lossy versus lossless distinction we made earlier. For practical, real-world BCI applications, where the goal is functional control or communication, and the subsequent decoding algorithms can often tolerate reasonable, non-critical reconstruction errors. Lossy methods like our CAE are, frankly, far more feasible, maybe even the only feasible path right now for high-density systems. While lossless schemes offer that tempting, perfect reconstruction, their inherently very low compression ratios make them entirely unsuitable for handling the massive, continuous data streams generated by systems with hundreds or thousands of recording channels. Our optimized lossy approach represents the pragmatic and necessary path forward for enabling functional, high channel count BCIs.
Lossy is the practical choice here.
And finally, just to reiterate the distinction one last time, our work is fundamentally distinct from spike compression. While spike compression methods can sometimes achieve even higher apparent CRs, you might see numbers like 900 plus reported. They do so by only processing and transmitting information about discrete, relatively infrequent spike events. They throw away almost all the signal between spikes.
They're compressing sparse events, not a continuous signal.
Exactly. Our work focuses on compressing the raw, continuous LFP signal, which, as we discussed, is like a constant information-rich waveform reflecting the collective activity of large neuron populations. Compressing this kind of continuous dense signal down to a CR of a 150 while maintaining such high fidelity for reconstruction is a substantial technical advancement. It represents a significant breakthrough specifically for LFP-based BCIs, opening up new possibilities for decoding cognitive states and intentions that might be primarily encoded in these LFP patterns.
That puts it all into perspective beautifully. It highlights the unique challenges of compressing LFPs and why this solution truly excels in that specific important domain. So let's zoom out one last time. If we connect this to the bigger picture, what's the ultimate, maybe profound impact of this kind of technological leap? What does this mean for the next generation of BCIs, and perhaps even for our fundamental understanding of the brain itself?
Well, if we connect this to the bigger picture, this technology isn't just about making existing BCIs a bit better. It is, I think, about fundamentally enabling the next generation of BCIs. It directly tackles those two critical bottlenecks we identified right at the start: the communication bandwidth limitation and the dangerous power dissipation, heat issue. These have been persistent, major hurdles holding back the development and deployment of high-density, real-time, and truly wireless neural recording systems for years. Without an elegant and highly efficient solution like this CA on Raman system, the full incredible potential of recording from thousands of channels simultaneously would likely remain constrained, limited by the sheer inability to process and transmit that vast amount of data efficiently and, most importantly, safely from within the body or a small head-mounted device.
It unlocks the potential of high-density recording.
Precisely. By providing highly efficient and remarkably accurate compression right at the edge, within the implantable or head-mounted device itself, this work paves the way for BCIs that are not only exponentially more powerful in their ability to decode complex brain activity, but are also inherently more practical, much safer for long-term use due to lower power and heat, and genuinely feasible for implantation or comfortable wear. This means we're moving much closer to realizing those goals of advanced cognitive decoding, allowing for incredibly nuanced and sophisticated control of assistive devices, or maybe even new forms of communication. But beyond the immediate applications, it also opens up opportunities for deeper, less invasive scientific exploration of the brain in more naturalistic settings. Being able to record high-fidelity LFP data wirelessly and efficiently over long periods could offer unprecedented insights into how our thoughts, intentions, learning, memory, and even consciousness manifest as patterns of neural activity. It moves us significantly closer to a future where BCIs can genuinely revolutionize not only how individuals interact with their environment, but also how we fundamentally understand the human brain itself.
Wow, what an incredible deep dive into a truly revolutionary piece of technology. The sheer brilliance, really, of combining these advanced convolutional autoencoders with the unparalleled energy efficiency of the Raman TinyML accelerator, especially with its innovative tricks like stochastic pruning and dynamic memory overlap. It genuinely transforms neural data compression for BCIs. Like you said, this isn't just an incremental step. It feels like a profound leap forward, making these incredibly complex interfaces practical, safe, and truly effective for people. And so we're left with a really provocative thought, aren't we? Given this dramatic increase we've seen today in the efficiency and the potential miniaturization of brain-computer interfaces, what new frontiers in human understanding and our interaction with technology might this unlock next? I mean, just imagine a future where the data flowing directly from our thoughts can be so seamlessly, so efficiently transmitted. What incredible possibilities from those advanced medical treatments restoring lost senses and movement to entirely new forms of communication, maybe even human-machine collaboration we can't even conceive of yet. What possibilities are now genuinely within reach? This deep dive certainly shows us that that future might be closer than we think. That's all for this deep dive. Thank you so much for joining us. We hope you feel a little more well-informed and maybe genuinely inspired by the incredible innovations happening right at the intersection of neuroscience and engineering. Until next time, keep digging deeper.